Hello, everybody. Welcome to this next seminar of the GReTA series. It is a pleasure for me to introduce the speaker of today, Pablo Arrighi. Pablo is a full professor at the University of Paris-Saclay. He's the leader of the QUACS group, the Quantum Computational Structures of the team belonging to the team of formal model laboratory, and he works mainly in quantum computing. And we'll speak today about this topic, which looks very intriguing from the title of the talk, Past and Future, What's the Difference? Please, Pablo, the spot is yours.
Okay, thank you. Thank you for the invitation, the introduction. Let me just add that currently I benefit from a détachement at INRIA, which allows me to be a full-time researcher for a couple of years, and that's a great luxury. So I wanted to say that. So yes, perhaps the title of the talk is a bit unusual since GReTA is focused on graph rewriting models. But the point is that I will precisely address this question of the difference between past and future through a toy model based on graph dynamics. Okay, so an expected application, if you like, of graph dynamics. Let me also specify that this is joint work with Gilles Dawek, so a research director at INRIA and professor at ENS Paris-Saclay, and Amelia Durbeck, who used to do her PhD thesis with me and is now a postdoc in Lille. Okay. So the plan of the talk is to, explain which problem we are trying to solve. I mean, the difference between past and future. Perhaps to you, it seems that there is no problem. It's quite clear what the difference between the past and the future is. But I will tell you that there is a problem and that there is a solution to be found. And that the current solution has problems that need fixing. And later I'll be talking about the beginnings. That's an even more mysterious topic, if you like. Okay, let's go. So, okay. So, first of all, I want to emphasize that this talk is about the difference between past and future. So the arrow of time, that is, yes, when we go towards the future, when do we go towards the past? It's not about the difference between time and space, for instance. I just assume that here it's clear. Okay, so past and future. So for us, it's quite clear that we can only go towards the future. We cannot get back to the past. But when we sort of scratch our head and think about why it is that we cannot get back, well, we start to come up with arguments like, okay, but look, if I break this glass, it's broken, and now I cannot just make the glass back. So if you like, our intuition sort of relies on the idea that there are more explosions in nature than implosions. Yeah, we do see implosions happening at times, but they are very rare events. For instance, if I have a little toy particle picture here, so those are particles, those are the speed vectors of the particles, and I hit the button play on YouTube, and now the physical laws start to apply. Well, what I will see is that these 4 particles, boom, they explode. These 2, boom, they explode. Okay, maybe sometimes there is some odd implosion of three particles that gather together, but those are rare events. So this is roughly the intuition that we have. Okay. Now, the issue that we have in physics is that the laws of physics themselves, they don't seem to make a qualitative distinction between past and future. In particular, for the physics law, they are reversible, all of them, all those we know. And so if you can go forward, you can go back. Yes, what do we mean by that? We mean that if I look at the configuration at t+1, there is enough information to work out how the physical system was at time t. If you like, the forward evolution has an inverse. Okay. And in fact, the situation is even more dramatic, if you like. The laws of physics are not only reversible, they are in fact time symmetric, meaning that the inverse physical law exists, and in fact, it's sort of the same as the forward physical law. Let me just make this a bit more precise. Well, here I just, let my particles evolve, okay? Those explosions sort of happen, fine. But let's say that now I grab each particle and I just flip it back towards towards where it came from. So meaning that I just toggle the speed vectors here. For instance, this particle was going up, well, now it's going down. Okay. And now I let the same physics law apply. Well, these four particles, for instance, they will just gather again. And if I flip the speed vectors back again, well, I'm really back to the initial situation. Okay. So there is this mathematical relation that, well, this sort of commutative diagram here that characterizes time symmetry. Or if you would just want to speak of this in a more continuous setting, what you would do is you would just take some PDE or anything that describes your physics. And if it's time symmetric, basically what that means is that you just grab the t inside your equation, substitute it by a minus t, and you will just find that you have exactly the same equation. So here we are. We have a phenomenon in everyday life that is quite clear. It's the difference between past and future. We experience it very, very clearly. However, our physics laws, they seem to say quite the contrary. I mean, they just don't see a difference at all. Okay. And that's a bit annoying, because after all, what's the point about physics? The point about physics is you come up with laws that will explain your everyday experience, right? Your everyday phenomena. And here it seems like, okay, it's not the case. Your laws, they just don't explain a very basic phenomena, which is the difference between past and future. So there is an effort here that needs to be made to close this paradox. Okay. And this effort was done by Boltzmann in 1896, right? He basically formalizes our intuition. He's sort of saying, well, yeah, it's not really that we cannot go back to the past. It's more like it's hard to go back to the past. He introduces a quantitative difference between the past and the future. He points out to the quantitative difference. And roughly speaking, this quantitative difference is precisely what our intuition was telling us, is basically saying, yes, as I go towards the future, more explosions happen than implosions. For instance, here there is like two explosions and one implosion, right? +2, -1, +1. So something is raising here. Some sort of disorder is raising here. Okay, if you like, this was more orderly, and this is more disordered. Okay. So that's the intuition, but we can make this way more precise. That's what he does. So let me just briefly recap what Boltzmann's proposal is. So he defines a quantity called entropy. It's a quantity it's a function that takes a macro state and gives you back a number. Okay, so what is a macro state here? A macro state is whatever observables you have at the macroscopic level. So for instance, here I've got a glass of water, and we just dropped some wine here, and the wine has diluted, but it's over there at the top left corner of the glass of water. And that's all we know. That's our state at the macro level. At the macro level, we are aware of this situation. Here are observables. Okay. So what's the entropy of that macro state? The entropy of that macro state is the log of the corresponding microstate. What does that mean? Well, technically, the molecules of wine, they could be here or there or there or there. Okay, this is like a 4x4 glass of water, sort of discretized glass of water. You could imagine a way more complex situation in real life. But here in this little drawing, there are 4 possible microstates. And then I need to take the log of that, so that would be 2. Okay. Okay, so that's the entropy of my initial state. And then what is going to happen, obviously, is that the molecules, they are going to dilute in the glass of water. And so now my situation at the macroscopic level is that, okay, I've got a pink glass of water, it's all diluted. So what's the entropy of that? Well, now my molecule could be at the top, but they could be also at the bottom. And since this is a 4x4 glass of water, and I've put just the molecule here to simplify, then I've got 16 possible microstates. So that's yeah, if I take the log, I'm going to have 4, right? So I see that the entropy, as defined by Boltzmann, has augmented. But to say that entropy augments towards the future is putting it the wrong way around. That's really what Boltzmann does, is that he actually defines the future as the direction of increasing entropy. Okay. Right. So this is the solution, the currently adopted solution. It dates back to 1896. But this solution, this Boltzmann resolution of the paradox, has a number of problems. Okay. So the most blatant problem, and this is something that has been pointed out many times in the literature. There is a whole book about that by Albert in 2001. This is often argued as the big open problem about time. For instance, in the Rovelli papers that I have here. By the way, to me, this issue was it was brought to my interest and conscience by Carlo himself. Yeah, so the main problem with Boltzmann resolution is that it assumes a low entropy initially. I mean, the resolution is basically saying, look, I hit play, I apply the laws of physics, and wow, entropy raises. Okay, so therefore, the dynamical time of applying the laws of physics, okay, it raises entropy. So this is the future as direction of raising entropy. That's fine, but the issue is, how come you started from a low entropy at the beginning? And that's I mean, for entropy to raise, you need to start low. But the states of low entropy, they are quite unlikely. Okay, so let me just emphasize this point again. What are the chances that if I give you a glass of water with some molecules of wine spread out in the glass of water, what are the chances that these molecules of wine are all gathered at the top corner of the glass? That is extremely unlikely. Okay, and now if we think about this at the scale of the universe, the chances that the universe starts in a very orderly situation is extremely unlikely. So if you like, this is the Boltzmann resolution is not exactly of the form, oh, here is your physics law, they imply this phenomena. It's more of the form, here is your physics law, now assume that God initiates the universe in a extremely unlikely situation that is radically ordered, then this implies your phenomenon of past versus future. Okay, and if you drop this assumption of a very low initial entropy at the beginning, well, what you have is your generic state is already of high entropy. Okay, and if you're already at high entropy, then entropy cannot raise. Okay, so because there is no past, there is no future. Okay, right. So that's like the top problem that needed to be solved here in terms of past versus future. But there are others. For instance, another issue with the Boltzmann resolution is that, okay, you start with a low entropy, entropy raises, but if you wait long enough, it's going to decrease again and raise again, etc. I mean, yes, I initiate my glass of water with a drop of wine here at the top corner. The wine spreads out, but at some point it may, I don't know, bounce off the boundaries of the glass and gather again. Okay, that seems extremely unlikely in your everyday experience. However, there are theorems that tell you that this is actually going to happen. In the continuous setting, in the sort of classical mechanics continuous setting, this is the Poincaré recurrence theorem. But if we just stay in the discrete setting, it's kind of obvious that in a closed system with finite degrees of freedom, if you just iterate a bijective function, I mean, I just go from one configuration to another, to another, to another. At some point, I run out of configurations, like there is no more arrangements of molecules in my glass of water, and I need to get back to an already visited configuration. And I need to get back to the beginning, to the early configuration. I cannot go back to an intermediate configuration. Otherwise, my dynamics would not be reversible, right? I mean, the aim of the game here is to explain the arrow of time from reversible dynamical laws, right? If I was to go to an intermediate configuration, then I would have a situation where two configurations lead to one. So I would break injectivity of the evolution. Okay. So anyway, the point is that yes, the entropy curve is actually oscillating. So that's quite disturbing because it's like, oh, this is the direction of the future. Oh no, by the way, now I'm going towards the past. Okay, it's kind of a bit problematic. Yeah. Okay. So there is a third problem in the Boltzmann resolution, which is called Janus time. It's been pointed out quite clearly by Goldstein in 2016. And the point here is that, you know, I put my drop of wine in the glass of water, fine. I sort of let the physics laws run, and okay, entropy raises. But let's say that on YouTube, I have this reverse play button here that sort of says, oh, I'm gonna apply my reverse laws, my physics laws, but in reverse. Okay. Well, it turns out that the wine is going to dilute too in the reverse direction. And so entropy will also raise in the reverse play direction. So there is this time here where, you know, future could be that way, but it could also be that way. Okay. Just to illustrate this again. So I initiate the system with a drop of wine, but now instead of applying my physics law, I apply the reverse physics law. So this particle, instead of moving right, it goes left. Okay, so it goes left. It's going to bounce off the wall, and then it's going to sort of spread and dilute. Okay, so the point is f-1 also raises entropy. Okay. Okay, so plenty of problems. Let me try and tell you how to fix. Well, let me give you a little toy model that fixes two of these problems out of the three. Okay. So the problem, the toy model, it needs to be reversible, right? And moreover, it's going to be local. It's going to be respectful of the idea that there is a limited velocity of light. It's going to be a very, you know, rough simplification of it all. I mean, it's going to be a one-dimensional world. Okay, just remove the, you know, X, Y, Z, remove Y and Z. We're going to be in a one-dimensional universe, discretized with a periodic boundary condition. That is, it's just a universe made out of just a circle. And well, some particles are going to be living in that circle, just so that, you know, some activity happens. And there's going to be two types of particles. The left moving particles, the ones that want to hop left, and the right moving particles, which sort of stay where they are, but they are still right movers with respect relatively to the left movers, if you like. Okay, and what happens in the model is this. One step of the evolution f is given by it's decomposed into two steps. One step where the particles move, and one step where they interact. Okay, it's like very typical of the lattice gas automata models that are in physics, where you have this advection and then interaction step. And so let's look at this on this example. Here, what happens is that you go from this situation to this situation. How? Well, just the left moving particles, they just move. Like this particle wants to move. Well, it moved. This particle wants to move. Okay, it moved. Okay, so that's what happens in this first step. Like all the left movers move. They move at once, synchronously. It's a synchronous graph dynamics that I'm describing. Okay, and in the interaction step, the graph is going to be shrinking or expanding, again according to local reversible rules. So in fact, it's just one local involutive rule that is going to apply here. So if this pattern in the graph is detected, it's going to be mapped to this one. So that means that this node is going to split into two nodes. It's going to infant two nodes in the graph. And if this pattern is detected, well, those two nodes are going to merge into one. Okay. So for instance, here in this second step, we detect this pattern here. So these two nodes, they shrink like that. Okay. This is a model that the model I'm describing here is actually a variant of a model by Haslacher and Meyer from '98. We did a variant because we were incapable of making proofs in their model, whereas we are capable of proving what we want in this model. Here, the description of the model is very informal, and I'm aware that this community is very much interested in the details of the formalism of how you would actually define these dynamics. But I think I gave a previous talk about the sort of causal graph dynamics and reversible causal graph dynamics formalism. You need to be quite careful, really, if you want to define this properly. You need to name your nodes with some naming algebra and so on. But anyway, this was the subject of another talk, and here I'm really wanting to focus on this sort of application, unexpected application of these graph rewriting models. Okay, so anyway, so let's just iterate this second time. So we saw that this configuration was going to this configuration. What happens now? Well, the left movers, they move. So he's moving there. Okay. And so that's what you get. And now you detect this pattern. This pattern is going to cause shrinking of two nodes, and this pattern, this node is going to expand into two nodes. Okay. So if there are questions, I don't hesitate to ask them. Okay. Right. Okay, so you could just, go on, just iterate your dynamics. And the kind of question that we may wonder about is what is going to happen to the size of this little toy universe under this reversible dynamics? Because sometimes you see it shrinks, sometimes it expands, and the rules that do that, it's just these involutions here. So there seems to be as many good reasons to expand than there are to shrink. Okay. And yet, we were able to prove for this model that, in dynamical time, as you apply your graph dynamics, the curve for the size of the graph is U-shaped. Okay, so meaning that whatever initial state you take, so it's not exactly whatever initial state you take, you need to have at least two kinds of particles, one right mover and one left mover. But okay, almost whatever initial state you take, the graph is going to grow in size like this. Okay, and if you hit reverse play, it's going to grow in size too, towards the back. Okay. This talk that I'm giving is introducing many sort of physics concepts, and perhaps that's what makes it a bit could make it hard depending on the audience. But really, at the technical level, this proof here is exactly where the difficulty lies in the paper. I mean, to prove that this model, besides its reversibility, always grows, is the thing that was impossible, that we didn't manage to do in the Hassler-Meyer model, and that we were able to do here. And to do that, you need to use really computer science-like proof techniques, where you identify some number that is decreasing and hitting a minimal, and from there on, you know that your graph is going to always increase in size. Okay, so I'm not going into that, but this is really the technical part of the paper. Okay. And then then you can look at entropy. Okay. And you will see that entropy basically follows the size curve. That's sort of easy to see, because let's say that I have a particle, but I don't know where it is in this two-node graph, like just like earlier on when I had this molecule of wine in the glass. Well, okay, what's the entropy of this? Well, what are the corresponding microstates to this macrostate? Well, the corresponding microstates are, well, the particle could be here going up, or it could be here going down, or maybe it's here going up, or here going down. Okay, there are 4 situations. Okay, well, now let's say that the graph grows in size. And because my dynamics conserves the number of particles, what happens is that now, I don't know where the particle is, but there are more places where I could put it. In fact, there are 8 places. And so there are more microstates corresponding to that macrostate. And so entropy, in the sense of Boltzmann and in the sense of the entropy of a gas, raises as the graph grows. Okay? Right. So the corollary, therefore, is that regardless of the initial state we start with, the entropy curve is U-shaped. And so let's look at the problems with the Boltzmann resolution that we've had. The main problem was this strong hypothesis of a low entropy initially, this God-given order state that was initializing the universe in the Boltzmann resolution. And that was quite a sort of unlikely assumption. Well, this problem is solved here because here, whatever the initial state you start with, you know that the entropy curve is going to be U-shaped. It's a consequence of the laws that the entropy curve is going to be U-shaped. You don't need to make any weird assumptions about that. And so now you're back to having an explanation of the phenomenon, past versus future, that is derived just from a law. You don't need a sort of God-given, rather unlikely state. If you like, the point here that is made is to sort of explain where the low entropy comes from by this graph dynamics. Because what physicists from thermodynamics will tell you is that, yes, of course, I mean, if you want to observe entropy grow, what you can do is you put your gas, you just press it with a piston, then you pull out the piston very fast, and now you have a sort of orderly situation of the gas that is concentrated somewhere, and then entropy will grow as the gas expand. Okay, that's fine, but this pressing the piston and then pulling it out is a sort of external thing in this explanation, and it's an external thing that is not itself reversible, right? And here in this little toy model, what you have is that you have a kind of compression of your physical system as as the size of the graph goes to a minimum, and then bam, the graph expands, and that's sort of where the order was created and liberated to become a disorder. So, but the point is, in our model, the compression mechanism and then its release, they are fully reversible, right? It boils down to this little rule here that is fully reversible. So if you like, it's like you have a piston mechanism, but the piston itself is fully described as reversible. And that sort of answers a question that is sort of implicit, or well, actually pretty explicit in a Carol Chen paper of 2004, because this idea that it could be a sort of expansion of the universe that is the cause of having things that are ordered that are going to go into a disorder, that's an idea that is already present here in this paper, Carol Chen 2004. However, they ask the question whether expansion itself is a reversible mechanism or can be a reversible mechanism. And in this toy model, expansion is clearly a reversible mechanism. Okay. Right. So another problem that we saw about the Boltzmann resolution was that the entropy curve was sort of oscillating. Well, here, the entropy curve is not oscillating. It's U-shaped. There's no oscillation. It's not periodic. Great. Okay. And really, it's, if you try and sort of think a bit more about that and where does that come from, the recurrence theorems, this problem 2 in the Boltzmann resolution, that was always coming from considering a bounded size system. That's when you get into recurrence. Whereas here we have finite graphs, okay, but these graphs, they can grow, they can shrink, and so if you consider they are of unbounded size, and so what happens is that if you consider the whole space of every graph, it's an infinite set, right? And this is how you escape this question of hitting a maximal entropy. You never hit a maximal entropy, and so you never have to oscillate. Okay. Right. And what about the third problem? The third problem was the Janus time problem. And that problem we don't solve. We still have it. Okay. So let me just tell you a bit more about this Janus time problem. And in fact, make it even more dramatic, perhaps. By the way, this is not a concept that we came up with. This is something that exists in the literature for quite a while, and there is in fact a whole book by Barber that discusses this this idea. The idea is quite mind-bending. I mean, if you think about it, we are here having this Visio conference 13.7 billion years after the Big Bang. Okay, and we see time going forward in our reference frame that we've chosen. However, this idea of a Janus time is the idea that if you go back to the Big Bang, and in fact, if you go back 13.7 billion years before the Big Bang, perhaps there may be some beings there that see entropy raising towards what is our past. Okay, so they would experience time going in the other direction, and so this is why it's called Janus time. You have twins, one seeing time that way and another seeing time that way, perceiving time, physical disorder increasing that way. Okay. So I just want to emphasize here that there is in fact, in this talk, little by little, we see that there are really two kinds of times. There is the dynamical time, which is the one of, I iterate my function f, I iterate my physics laws, and I could reverse it. Okay, it's this axis. And there is the entropy time. It's the raise of disorder, the raise of entropy. So which is sort of the vertical axis here, because along the vertical axis raises entropy. Okay. Right. So no idea whether I mean, this sort of crazy Janus time thing is true or not, but it's certainly true in this toy model that we've presented. And it can be fun to look at what happens at the beginnings of the toy model. I mean, in this region of low entropy. So yeah, let's talk about the beginnings. Okay. Yes, let me just defend myself here a little bit. Yes, I will be now talking about the beginnings of time, the beginnings of this toy universe, etc. That perhaps seems a bit yeah, not very cautious. But okay, look here, we are really talking about a very tiny, toyish universe with a couple of rules. And so, you know, this is a thing that you can put in your computer, you can run it. You can run it forward, you can run it backwards, you can look at the moment where the graph is small, and you can just draw conclusion about your little toy model. And really, there's nothing that crazy about that. It's just a little toy model, okay? So let's see what the toy model would tell us about the beginnings. Okay. So, for instance, we could ask ourselves, was there a beginning of times? Okay. Yeah, I don't know. Yeah. What started time? Right. Big question. And here there are answers, but there could be different answers depending on what you mean by time. And this is why we could say that there are two tales about the beginnings of time that we can make. One tale if we focus on entropic time, and another if we focus on the dynamical time of hitting play and running your YouTube video of the physics. Okay. So if we focus on entropic time, the thing about disorder increasing. Well, entropic time is a half-line in the sense that at some point entropy was minimal, was low. I mean, it cannot go further than that. Entropy is, remember, it's a number of micro configurations corresponding to a macro state. I mean, this thing is it's an integer number, a positive integer number. You cannot go below zero. And so you start from a small number here, and then entropy grows. So in terms of entropic time, there is a kind of beginning of time. It's a half-line. However, in the explanation that we've given here, we see that this half-line, in fact, is a kind of branch of a U, right? We saw that this half-line is in fact like two branches of a U, and as we sort of unravel the U, we see that, okay, entropic time comes out from zero, but not for no reason. I mean, it comes out from zero because it's actually U-shaped. And so there was a moment where it was minimal, but this comes from another branch of the U. Right. So we see that this beginning of times story is perhaps better narrated with respect to the dynamical time axis. And the dynamical time scale is basically to say, look, no, there is no beginning of times. Time is B infinite. It's a B infinite line. It goes from minus infinity to plus infinity. End of story. Okay. So now let us try and think about not the beginnings of time, but the beginnings of matter, like of what things are made from. Because yeah, I mean, some of us have kids, and the kids, they keep on asking questions. They go through a period where they're saying, oh, where does Dad, where does the table come from? Well, it's made from wood. Well, okay, where does the wood come from? Well, it's carbon. Where does carbon come from? Oh, okay, it's look, it all comes from the Big Bang. Okay, but where does the matter from the Big Bang comes from? Now you're like, kid, I'm sorry, I don't know. We don't know about that. Okay. Well, in this model, we kind of know. We know in this model we know. In this model, it's clear that this minimal sized graph, they come from a larger graph earlier on in the past that sort of shrank to a minimal size and then expanded again. Okay. So if we answer our kid in the dynamical way, I mean, with respect to dynamical time, we have to tell him, look, it's a big bounce. Big bounce, right? Big bounce is a term that is well known in general relativity. And there are actually Einstein field equations solution that are big bounces by Sakharov in the 80s, Hartle and Hawking, 83. And it's basically telling the story of a universe that boom, crunches into a smallish thing and then bam, big bang occurs. Okay. All right. Now the problem may be the thing that makes this this dynamical time scale a bit ugly, a bit problematic, perhaps, is that it's very. I mean, if you draw a graph with particles at random, typically it will increase in size. Typically it will be found here and up, it will increase in size. I mean, as we said at the beginning of the talk, we usually see explosions, so not so many implosions. I mean, it's kind of, you know, your son may look at you and say, really, I mean, this whole universe collapsed. That's really weird. That's really unlikely. I mean, I don't see many things collapsing around myself. So perhaps to answer this question, it's better to adopt the entropic time scale. Okay? In the entropic time scale, you know, we experience a big bang from a sort of minimal entropy time, but this twin universe here, the universe that to us lives before the Big Bang, these guys, they see entropy rising that way, so they also experience a Big Bang, right? They just see a Big Bang, just like us, really. Nothing that crazy. No big crunch for them. For them, it's a Big Bang. Okay? So if you take this, the point of view of entropic time, what's happening is more like a big double bang. Like there is a Big Bang here, a Big Bang there, and the two are connected by the matter, their use. So if you like, our birth uses the matter which is at the past of their birth, and reciprocally. So it's a kind of double birth in entropic time. Okay, so yeah, so just so this these sort of tales are quite fun, and so I wanted to share them. Anyway, at the end of the day, so we tried here to give a sort of physics-like explanation of the phenomenon between past and future. Physics-like explanation is, okay, you have some laws and they imply the phenomena of past versus future. You don't try in physics to explain why the laws of physics are as they are. You don't. You just try and give some laws and try and see whether they imply the phenomena. Here, the sort of flows we are considering are sort of, reversible graph dynamical systems. And basically, we are showing that taking some laws that are reversible, local, that shrink and expand space, what you see then is a difference, a quantitative difference in terms of entropy between past and future. And you have this bonus of having a sort of dynamical time causation of the beginning of entropic time and the sort of creation of a universe from a twin time symmetric other universe. Yeah. So that's what I wanted to tell you about.
Thank you very much, Pablo. So there weren't questions on the chat during your presentation, so it's open now, the discussion phase. Thanks, Santiago. And okay, Nick.
Thanks, Pablo. Quite a nice toy model. Could you bring back the slide where you define the rules again? Just because I'm trying to understand. So let's say you start from you have some semantics for your graphs themselves. So you say they consist of, positions on a circle, and then you have a decoration. I guess you start from a state with some certain number of initial such markings, no? That's part of your model. You say, for example, I start with 6 sides, like here.
Yeah,
like for
for
example,
the
the bottom
theorem
left.
to apply, you can start from any number of sides. Yeah,
And
yeah, bottom
certain
left.
pattern
Okay.
of marking.
So
yeah.
you're going to have names for your nodes. This is going to be node U, V, W, X, Y, Z. And you describe edges between these name nodes.
Right.
And then you have a sort of function that assigns a state to each. Yeah. Also, these are graphs with ports, right? They actually the edge. I mean, each node has a port A and a port B, and this edge, for instance, is going to be between port A of this node and port B of that node, right? Because the particles, they need to know whether they are going through port A or port B.
Fine. And then basically you say each of the rules that you can fire will necessarily modify the size. The first rule enlarges it, the second one shrinks it, right? But the additional information is that you apply these rules synchronously. So you had this sort of idea. Somehow you're ensuring that the model that is unambiguous to fire the rules locally. Is that correct?
Yes. So okay. I mean, if you just apply some f, it may be that in one step nothing happens. For instance, if the particles are far away from each other, there is going to be no interaction rule fired. And so during that step, entropy will the size will not grow, right?
But I mean, that was one of my questions, exactly. Is it possible to draw a state which can actually not be modified?
Another of your question was about that do you mean whose size will not change?
I mean, sort of, maybe this is one should think about more carefully, but I mean, I'm looking at this and I'm thinking when I, for example, make myself particles far enough apart. I mean, I'm trying to see, I don't have a good intuition how it works as a synchronous application. It seems that you're saying this is a grammar in our language. If I, just from these basic generators, if I apply, there's a unique word I can apply in the generators to each, I mean, somehow each configuration gives me exactly one way to apply a synchronous rule. Is that what you're saying?
Yes, it's unambiguous. I mean, for instance, when you look at these patterns, they are kind of closed patterns, well delimited patterns. So they cannot overlap these patterns, and so there is no ambiguity of whether I should reduce here or reduce there, Okay, there is no critical pairs, if you like.
Mm-hmm.
So it's you could say it's a parallel rewrite strategy where there is no critical pair.
And so now, okay, now let's say, so for example, in this little picture here, you say the entropy is essentially the number of sites, more or less. I mean, because for each number of sites, you have a certain number of configurations. You're basically assigning each state with a certain number of sites the same entropy. Is that it? If I have 5 states.
Yeah, because the number of particles is conserved, entropy is quite related to the size.
Yeah.
I mean, entropy is the log of the number of ways to place your particles in the graph.
Yes, but I mean, you can overall only place the number of particles you have. So, I mean, I guess that limits the choices. Unless you don't assign entropy a higher one when you have this configuration where the 2 particles are on the same side. You say that is just part of overall number of configurations. You don't single out.
Yeah, we take as macro states the number of particles and the size of the graph.
Exactly.
Yeah.
So, but I mean, that would seem that
just also to answer the question about asynchronous rewriting. The whole aim of the game here is, from reversible physics law, see a difference between past and future. Now, if your strategy is asynchronous, then it becomes very difficult to understand what is determinism and what is reversibility, therefore. Right? So you sort of much safer in a synchronous rewriting system.
But then, like, even in this little picture, I would think that somehow I would have decreased my entropy when I lose sites, or is that a misconception? It seems like the transition seems to decrease momentarily.
When I draw the size curve here, you see that I draw it in a way that oscillates. I mean, it's sometimes your graph can shrink, but what we prove here is that ultimately it grows.
And so the statement you make is something of a combinatorial nature. You say that overall, on average, for a large enough graph, the chance to see a transition that increases entropy is higher than the one to see one of the shrinking possibilities, which is always there, no? Because you're reversible.
That is probably true also. But this is not something that we prove. I mean, we just really prove this statement.
Interesting.
That it grows. Yeah.
Maybe I leave also for others to ask questions. Otherwise, we can.
And Fjord, do you want to ask something? If not, no, considering exactly the things that you were discussing, Pablo, in these pictures, so this U-shape, I mean, can you give an intuition? So there is something conflicting in my view. The idea, one is the fact that the transformation is reversible, and second, the fact that definitely the entropy raises. So in my understanding, it should always be possible that then the entropy goes down again. So either is a matter of probability, or there is something I'm missing.
Yes. Okay. So something that helped us understand this precise point that you're making is to think of bijection over the integers that ultimately raises. So let's say that you divide up your integers between odd and even numbers, and you make sure that the odd numbers always go down, okay? I don't know, you just send 7 to 5 and 5 to 3, etc.
Okay. Mm-hmm.
And when they hit 0, you put them in the even numbers, and then you make sure your even numbers, they always go up. You send 2 to 4 and 4 to etc. So then you will have a. Now, if you look at the size, okay, you will find that even a big, any number ultimately raises. I mean, if it was odd, it's going to go down to hit the 0 and then go up.
Mm-hmm.
And if it was even, it will just go up.
Okay. Okay, but
So here you have a bijection.
Yes, I think I got what you mean. By composing this bijection several times, in the end, every number will be matched to a number larger than it, right?
Yes.
Provided that
Yes.
you compose it enough time. Okay, I think I got the
Exactly.
point. I've got the point. Thank you. Hans-Jörg, please.
Yeah, thank you very much for the presentation. I enjoyed it very much. My question is, do you have any open problems you would like to consider in this context? This is one question, and the other is, what would you like to look into more complex models having similar properties, or is this just a nice example you enjoy and it's okay?
Okay, so for instance, one thing that I said at the beginning was that the laws of physics are not only reversible, they are in fact time symmetric. Okay. Now, the model that I gave you here is reversible for sure, but it's not time symmetric. So one question is whether we could tweak this model to make it time symmetric and still be able to prove such a theorem. In the full paper, we have a sort of time symmetrized model, but and numerically it behaves like that, but we are unable to prove such a theorem. Okay, that's one of the things that that would be interesting to look at, and there are many others. I mean, this is a one-dimensional model, okay, and it would be really fun to have a three-dimensional model, for instance, and that we really don't know where to start.
I see.
Other questions is okay. Our law of expansion here is a law of expansion that is quadratic. I mean, the particles, there is less and less particles in the circle, and so there is less and less collisions, and so the universe expands. This toy universe expands less and less. It does expand, but it expands less and less. And when you look at, I don't know, if you ask some physicists what is the law of expansion for the universe, well, apparently it's a very complicated problem, actually. They say that in the early times of the universe, it was an exponential growth, and then it became a sort of polynomial growth, but we don't really know how to evaluate it. It depends on whether you look at supernovas or whether you look at, I don't know, I mean, it seems to be quite a messy answer. But nevertheless, our law of expansion is quite clearly quite unrealistic. I mean, it doesn't fit any observation or whatever. So it could be fun to sort of come up with little graph models where you sprinkle the right kinds of particles with the right kinds of interaction rules, and you try and have a realistic curve. I don't know, that would be fun as well. I don't know.
Thanks, yeah. I see.
Nick?
Sorry, just one last question before we maybe can stop the live stream. Because sort of intuitively, I mean, do you think it might be possible, just for the sake of argument, to also have a model where just individual transitions can be fired in each round, which still shows this behavior? Because, I mean, I understand you are in favor of the synchronous application, but is there any good reason to completely exclude the possibility of asynchronous application, which would be more like a microscopic model? I mean, it's kind of, this would then be more like an automaton, no? You would have essentially some states and some possibilities to transition. It would be no longer deterministic, no? I'm just curious why you chose something which basically is a completely linear evolution. It's not necessarily the only possible model, no? I mean,
so I think I'm back to what I answered before, which is that if your rewrite system is asynchronous, then in what sense can it be reversible?
That's exactly the question. Yeah.
Or in what sense can it be deterministic even?
And that's the point. So then you wouldn't necessarily have.
But yeah. So we are, in fact, this is exactly the question we are working on at the moment with Ludnel-Ménian and Marin Coste and in fact Gilles Dawek. We are trying to, first of all, just understand how a synchronous graph rewriting model can, in some sense, be deterministic. Yeah, be space-time deterministic. Because in at least in general relativity, there is this idea that you can evolve your surface, your space-like surface. You can evolve it here and then here and then here, etc. It doesn't really matter what your evaluation strategy is, and yet at the end of the day there is a kind of determinism, because after all you are just choosing a surface within a well-defined space-time, right? But this is the notion that is unclear in graph rewriting. What would be this underlying space-time, and in what sense are you deterministic with respect to that?
Right. That's a bit getting into this territory of the Wolfram Physics project. Yeah. So a little bit.
Well, apparently it could be something
I don't know about that.
So determinism could be clearly related to confluence when you have the asynchronous, but also to fairness. You cannot leave some part identical while rewriting only on another part. But if you have a system which is asynchronous, confluent, and fair, giving every piece the possibility of evolving, I think this is a good non-deterministic approximation of the synchronous parallel evolution. This could be just an idea. May I ask one further question, Pablo, about the one of the histories of the beginning? Is very intriguing. These are very intriguing, the Janus and the double Big Bang. But is the double Big Bang, I'm completely ignorant about the matter, is a possible explanation of the lack of antimatter in our universe, that the antimatter went to the other side of the Big Bang, something like this, just qualitatively?
Yes, thanks a lot for asking this. It's actually exactly the reason why Sakharov in the 80s proposed such a solution to the Einstein field equations. I mean, he wasn't bothered about a resolution of Boltzmann, solving the problems of Boltzmann's resolution of the. He was precisely worried about this this breaking of symmetry, this CPT symmetry breaking that you're mentioning.
Okay.
Now, I wouldn't be able to relate this to our model in any way. I don't know enough about that.
Okay. Me neither. It was just hand waving, but okay, thanks. There is indeed some relationship between.
Yes, there is a relationship there.
Okay.
Oh, yeah.
Thank you. Nice to know. Thank you very much, Pablo. Well, I think that we could now close the live streaming of the seminar, continuing in private. So if somebody watching the seminar on YouTube wants to join us in the Zoom meeting, the link, I guess, is available directly in YouTube. And thank you very much for the presentation, Pablo. And I understand the next GReTA seminar will be in 2 weeks from now, but I don't have at hand the name of the speaker. Maybe Nicolas, you...
Yeah, thanks, Pablo, again, and also Andrea for hosting. So the next speaker will be Patrick Stünkel. He will speak about comprehensive systems for software interoperability problems. So this will be more of an MDE type talk, and it's actually going to be co-located with a meeting of the MDE GDR here in Paris. So probably will be co-hosted with them. And